Okay, so I'm Barak Zackay. Thank you, Yair, for the introduction. I'm a student in the Weizmann Institute of Science. I'm a student of Eran Ofek and Avishai Galiam. And today I'm going to tell you about how to properly image subtract. So we have already seen that image subtraction is notoriously hard from both Yair and Or. And we'll first ask why subtract images, then we'll show why is it hard. We'll show the existing solutions and their problems, the problems that Yair showed. And we'll show our solution. Sadly, 20 minutes is not enough time to show the argumentation of why is it optimal. If we'll have enough time, I'll also show the outline of the derivation of why is it optimal. You'll have to believe in some sense. Okay. So we want to reveal the transients to the computer. The key word in this slide is computer. So you don't want your students looking on the transients. Okay, you want something automatic to detect them and flare your phone to say, please take a spectrum or something like this. So why do we subtract images? So we have a complex background object like a galaxy. I don't have a model for a galaxy. No one has a model to fit all galaxies miraculously. No one knows what's really on this image. All we see is what the telescope gives us. And what the telescope gives us has finite resolution. And worst, it has some obscure transfer function for the atmosphere and turbulent stuff. So we want to subtract images, i.e. we want to somehow get over the complex background. So we have a new image. We don't know if something here is new or not. We have no idea, right? This could be new, this could be new, this could be new. I don't know. And we have an old image that looks quite the same as the new image. And we want to understand that there is an excess flux here. That's what we want to understand. And we want to do it without assuming the shape of the galaxy or the image that is going on itself. And we have problems with artifacts. Now, why is that? Is a bit longer story. But actually, we don't even know that this is an artifact. Yair told me that he thinks this is an artifact, but he then didn't follow it. So Yair doesn't know.
Well, we didn't follow it spectroscopically. We have more images later where it comes and goes. So
okay.
Probably an artifact.
Why should it come and go if it's an artifact? It's hard. Okay. So I don't know. Why should artifacts that are with the atmosphere will return in the same galaxy? No one knows. It might have been an AGN. It might have been. You don't know, right? You truly don't know. Okay. Now, why is it hard? So for this, we have to write down some equations, but not complex ones. So we have a reference image, okay? And how does a reference image is generated? You have the true sky. It's convolved with the transfer function of the atmosphere. We call it a PSF, point spread function, okay? And added some noise. That's how an image is formed. The new image is formed the same way. You might not have the same image, but let's assume that you do have the same image. You just want to see if the new image is consistent with having the same sky as the reference. Okay? Good. Why is not just a minus? So if I have one transfer function for the new and one transfer function for the reference, and they are not the same, even if the image is the same, you're going to run out into convolving with a difference of transfer function. It's not zero. So this means that a star that was a point here that was squashed that way, and point here that was squashed that way, will look as a yin-yang thing in the image itself. Okay? So that's not going to work. Okay? But no one does a minus, because that doesn't work. So what are the existing solutions for image subtraction? The existing solutions for image subtraction, well, you have two approaches. This one is unpopular, so we'll regard it less, but this is the main thing. This is used by practically all surveys. Okay, it's by Allard and Lapton. We'll call it Allard and Lapton. And you take your new image, and you subtract something which is not exactly the reference image. You have the reference image convolved with something, and this something is computed via a very complicated way to minimize some residual. Okay? You have another solution of Avishai Galiam, which is not through an optimization problem, which is take the new image, convolve it with the transfer function or point spread function of the reference image. Take the reference image, convolve it with the point spread function of the new image, and subtract them. So this one has a point spread function which is equal to this to the point spread function of this thing. So that true image should cancel. In both, in fact, you try to cancel the true image. Here you will mathematically get a 0 of the true image. But it's kind of hard to judge. So I want a vote in the crowd. Who thinks this method is better than this method? This one is used by, I don't know, 99% of the people. But who thinks which is better? So vote for Allard and Lapton.
Depends what you want to do, right? No one method.
I want to detect TDEs. Who votes for Allard and Lapton? Brad knows. Who votes for Galiam?
I've papers with that method. So.
Who votes for Galiam? Okay. So the real answer is that no one is right and no one is wrong. So it's not even wrong, none of them. And this gives good performance. This also gives good performance. But in order to understand what's going on here, you need to actually see the real solution and understand what happened here and what is the problem. So let's go over the problems of Allard and Lapton, but not only. Okay? And the first problem, it might not interest all of you from the start, but for me, it was a real issue. There is no statistical argumentation. No one says, except in the headline of the paper, that what you're doing is optimal. There's no argumentation. And not only that there is no argumentation, it actually leaves subtraction residuals. So it doesn't match the PSFs correctly. So if you have a point source which is strong enough, you will see it's yin-yang in the images, even if it's not saturated. And those create, in turn, millions of false detections, which are then fed into machine learning algorithms and sifted by the machine learning algorithms, leaving, instead of millions, hundreds. And then you have human scanning. What is human scanning? It's student scanning. Okay? And lots of
students are human, okay?
And
go with it.
And transients are effectively missed. And especially TDEs, because TDEs lie on centers of galaxies. And on the center of the galaxy, you might have a bright spot which is as point source as a star. And stars, bright stars can leave yin-yang things. So you'll see a yin-yang in the center of the galaxy, and the entire galaxy vanishes, and you start, is that a TDE? I don't know. I saw 100 of these yesterday, and I don't know if it's a TDE or not. So TDEs are especially vulnerable to be missed. It's numerically unstable, so students probably don't know this because this thing will already not give you anything if the algorithm was numerically unstable. But if you try to run it by hand, it fails many times and gives you some ringing. And it's if you've ever seen the convolution artifacts, these kinds of artifacts. Okay. Now it returns also an image with large-scale correlations. Large-scale correlations means that if I want to test something local in one part of the image, I need to somehow consider pixels like the other side of the image because they have correlated noise. So I might need to some way take this into account. It's unclear how to actually find sources. So if the student sees a source, you will report a source. But if you want a machine to do it and you want it to be honest and you want to report this is 5.7 sigma detection and not 3.7, you actually need to do it in an honest way. It's also unclear how to prepare a reference. Right now, the magic of how to prepare a reference is take the best image of this field and take the 10 best images of this field. Whatever this nonsense is, it's unclear, okay? And it's slow, but, you know, slow is just, it's not slow enough to be prohibitive, but I have 5 minutes.
4 actually.
Okay. Then I better show my solution. So this is the optimal image subtraction. So what's going here? So first, what is a hat? Hat is a Fourier transform. Okay. And even though the solution is stated in a Fourier transform way, it's actually a local solution, so don't be afraid of it. Okay. So it's everything here goes locally. So there is something to be convolved with n. And this something involves the point spread function of the reference. There is something to be convolved with R, which is the point spread function of the new image. And it's divided in Fourier plane by this obscure thing. And I'll tell you what is the rationale of this thing. The rationale of this thing is to have white noise. Okay? So here is the performance of this solution. So you take 2 images and you subtract them. And you're left with this. So you might tell me, okay, but you have subtraction artifacts, but this is saturated, so there's no exit from saturation anyway, no information in saturation. This is saturated, this is saturated. This is a cosmic ray, this is a cosmic ray. And actually now you can test if a transient is a cosmic ray. Before you couldn't do it. With Avishai's method, it's quite hard to understand because cosmic rays look exactly like transient. It's a complete mess. But right now you can actually test because a cosmic ray still looks like a cosmic ray. You can filter it out. You can say what is a transient and what is not. And if you match filter this image, well, you will see sources, but these sources are the cosmic rays that you were supposed to filter out from the image before. And you can just say that there is no transients here. Okay? So you can take a computer, receive 2 images, and get a 5 sigma clipping. So you are left with essentially the cosmic rays and saturated stars and edge effects because Fourier transform doesn't like edges. Live with it. Okay. We can prove the noise. Actually, we constructed it to have white noise. We can prove mathematically it's optimal. I gave you only the intuition that it's white. It has white noise. It's numerically stable, so if I show you the solution again, okay, I'll show you the solution again. If I show you the solution again, you'll see that the division, you have division in Fourier plane. You should have thrown it back to me. What do you mean, division in Fourier plane? How prove that you do not divide by 0? So here I'm multiplying by something, and then I divide by something else. And actually, this is always smaller than this thing. So whenever this goes to 0, this goes to 0 even faster. So this expression, this entire expression, is actually numerically stable. So it's not going to explode some way. There's no way for it to explode. Okay. And no subtraction residuals, that's by construction. The constant image actually is removed completely mathematically. It's fast, it's in closed form. There's no complex minimization of images. So it's actually faster than reading the images from memory. It has a closed form reference, which I'll show in a moment. And it is local, so you can apply, you can use spatially varying PSFs, which are a feature of all existing solutions. Okay. I told you I'll tell you how to prepare a reference. Again, I have much more robust in argumentation, but given the time, I can only tell you what this is. So you have a reference, you match filter it with its own PSF, you somehow miraculously sum this up, okay? Summation in Fourier plane and summation in image plane is the same thing. And then you arrange white noise. You go to Fourier plane, you ask what is the standard deviation of this thing, you divide by the standard deviation, you have white noise in Fourier plane, white noise in Fourier plane is white noise in image plane, okay? And again, you can show that this thing is optimal for any further signal processing. Actually, it's optimal not only as a reference for image subtraction, it's optimal as a coaddition method. It's optimal for testing in galaxy shapes or whatnot you want to test on the image. Actually, it's optimal no matter what you want to test on the images. And it can truly summarize an entire survey into an image. So if you have 1,000 images of the same place of the sky, you can summarize all the constant in time information into one image and know it's there. Whatever you could do with this set of 1,000 images, you can do with one. So this is a killer app on its own. And its PSF is actually sharper than the best PSF in the dataset. Now that sounds suspicious, so I'll just show an image. So what's going on here? So here I have 4 images, okay, with different things. So this is simulation. In short, you'll see real data. But you have different things, okay? This is what happens when you just add them up. This is what happens when you properly add them up. Judging from this, I could not tell anything. But what happens if the PSF varies more wildly? Let's say like speckle images. Okay, speckle images are what happens if you take a telescope and you image very, very fast a point source. Okay, so this is a point source.
Binary.
It's a binary star. Okay, but from this you wouldn't tell. And so this is the regular addition and this is the proper coaddition. Now this is white. I'm telling you that this is on the same grayscale. Okay? So if you want not to throw all your information out, use proper coaddition, not regular coaddition. And showing the crosscut of these images. So this is a cut through this thing and this thing. Okay. Showing a cut, you see that even on the Gaussian things that you add Gaussians, even there you have a better PSF. Actually better than the best PSF in the set. Okay. And you can see now you can see the regular coaddition, the regular addition versus the proper addition. Okay. And on real data, this is an image we acquired with not enough contrast. This is a binary star, you can see. On the screen, you have enough contrast. So this is an image acquired with a 40 centimeter telescope in the middle of the city. And you could separate 2 binary stars 0.7 arc seconds in separation. And it's unambiguous, and you can do it. And there is a closed formula for doing this. And the conclusion is that image subtraction is no longer an issue. And given the fact that I don't have time, I will not show the derivation. But I'll leave it here so when people ask questions, you could read.
Okay, thank you. Yeah.
So assuming you have the image and you know perfectly the point-spread function, is it possible to decompose the image and sort it by this?
No. Why? Because this information is not there. When you deconvolve the image, you deconvolve the image with the noise. Deconvolving the noise means that you divide the noise by the PSF in Fourier space. This means that you divide the high frequencies by 0 which means that when you come back to the image space, you will be left out with something like this. Okay? And this is not even deconvolution. This is the Phillips and Davis. This is the first method offered for image subtraction. Okay? Deconvolution is not... It sounds like, okay, I'll solve convolution by deconvolution, but this information is not there. It's not measured by your telescope. You are inventing it.
Looking at that this method is better, the method you're continuing to do for subtraction. So how much better is it really? How much of the TDE cost?
Well, I think that until we have a working pipeline with this method, you wouldn't know figures because, for example, we don't know how many TDEs we are missing right now. We honestly don't know because no one says this is a TDE on the image of the artifact that you are examining now, and you are students and you are tired and you want to finish the scanning because it's like guarding a base in the army. So
You can do simulated data sets like we did.
So I think that the best thing would be to have a working pipeline. With simulated images, I can tell you the performance.
Into real images and see which ones you recover with, how many you recover with, ones recovered in the current method, and maybe reach the rate gap.
So for that, I need a working pipeline.
Yeah.
As an observer, may can tell you something about simulation. The problem with simulation is that it's very hard to simulate everything in your process. For example, if you have fast feeding or just in the registration process of your images is not perfect, that will affect any method of the PSF estimation. So if you do everything correctly, then we promise that we will give you the best results possible. Rely on other things, other estimates.
But specifically, the image subtraction problem is doing problems on its own. So, but I won't have a better answer before we have a working pipeline because we don't know the performance of Allard and Lapton anyway now. Okay, so is that a fair answer?
So how do you, first of all, you're still sensitive to having the images properly registered to each other, right?
Yes.
And how do you, and you still, it's independent of the method which you determine the PSF of the image?
Yes.
Okay.
So Allard and Lapton do not rely on the PSF estimation for the subtraction, but they rely on it for the source detection. So anyway, you should have a PSF estimation. It's not.
And so when can we expect a working Python package that does this?
So Iran is having a MATLAB package that does this. I can give you I can give you simulation. I can give you code that if you gave it correctly, there is a thing called garbage in, garbage out. I can give you a code that if you give it garbage in the inside, it will give you garbage on the outside. But if you give it correct point spread functions, images perfectly registered, and the images themselves, it will subtract them correctly because it's a closed formula. But if you have all this, then you might as well just write this formula. It's a one-liner Python code. So take n fft.fft2.
So there is a source noise correction. And the
Source noise correction term is okay. There is more complications to it, but it's not like this formula is going to be any different. So it's a one-liner thing.
Does this mean you can actually combine images from different machines?
From different machines, you mean?
When you talk about your PR and PA, and you show
Yes. So if they image with the same band, i.e. they see the same sky, I don't care. I don't care.
Two different regions in the sky.
When you say two different machines, I don't know if you mean a machine in the X-rays and a machine in the UV. No, two machines that work in the same wavelength.
Two different optical telescopes that look at the same
Yes,
region
yes,
of
you
the
can.
sky,
Yes,
and, with
absolutely.
different resolutions, but they look at the same place, so you want to improve the data by combining.
Absolutely. I don't care what PSFs are there. It works even with speckle images. Those are the worst kind that you could imagine.
you have to have the pixels aligned to the same point in the star. It's not.
So alignment is a different problem. If you have many stars, then you can align the stars to the point of the
Right, this
center of
algorithm
light.
the image is already aligned.
yes.
The pixel level. So
Yeah.
the same pixel is aligned.
Yeah.
This is very hard to achieve in two different telescopes.
Right, the pixel scale is very different.
The main problem with
Anyway, you do
the
resampling.
with the transparency of the system. The registration is not
You can do
have a
resampling.
third of a pixel here,
You can register,
two-thirds of a pixel there.
you have white stars in the image.
Yeah.
Can I answer this? Can I answer this?
If you register HST to assassin. Okay.
How do you get this estimate?
Yeah.
I can turn this question back to anyone who uses observational astronomy. So PSF estimates are needed for coaddition, they are needed for subtraction, they are needed for source detection, they are needed for galaxy shape measurement, they are done essentially in every survey. They have their own PSF estimate. If it's working on their data, if it's sensitive, if it's correct, it's going to work.
What prevents you from fitting for the PSF simultaneously with fitting for the image? I mean, it's obviously
There's no fitting. There's a closed form. I don't understand.
Yeah, it's not optimizing.
Okay, I understand. Okay, I understand that here you can write it down as a closed form, and I understand that if you actually try to include a model of the PSF, you probably will not be able to write it down in a closed form. You have to just marginalize over possible PSF. But in principle, okay, it's more computationally expensive, but it's doable.
Marginalize over possible PSFs. So PSFs are generally measured from stars much brighter than the targets that you are trying to subtract.
Right, but you're saying that just have that as a free parameter and see what PSF gives you the best, the cleanest image of that.
But you can do another exercise. You can estimate the PSF error that you might get from a bright star and propagate it through the image and see, would it matter? And if the PSF was measured on a target which is much brighter than the image you are trying to subtract, then these PSF errors are going to be less than the noise in the image itself.
Minimization on PSF itself is not enough because there are infinite number of solutions to this problem.
Sure.
So you need another criteria.
Right.
And the criteria is given in this formula. It's not
But criteria for what?
so this is not noise maximization.
Yeah, it's more constrained. You have
Sure,
more
right.
free parameters.
Absolutely, you need to put in some sort of regularization. I understand that in general.
No regularization. Regularization is when you do the convolution. Regularization is something that you need to do when you invent information and you restrict your solution to be fair with some kind of fairness.
Sure, and if I'm going to invent a PSF, I have to, put some. Okay, if you would put a prior on my
Yes.
PSF, I could put.
Yeah. The PSF is a prior to something. Okay, but it's a well guess, right?
Okay, if I have already a good guess, then it simply constrains my search space, but I can say, okay, my PSF is allowed to vary from the
Yeah.
best estimate by a small amount if I believe my PSF estimation, but I can still, in principle, I can continue
Yeah.
to fit it modulo the condition
Yeah,
that.
but before all these complex solutions, you can just estimate what is the error in the PSF that you have just measured. And if you have a bright enough star, and bright enough is going to be much brighter than the galaxy you are trying to subtract, this is going to be negligible. You can estimate how wrong am I, and does it matter for this exercise of subtraction. If you encounter problems with the PSF estimate, then you need to be smarter. That's true. But I'm not sure this problem exists.
Okay, I think we should move to the discussion session. So thank you, Barak. Again.